All right. Welcome everybody to the Build Your Simulation Mechanical IQ. Today it's going to be myself, Dean, and my colleague Marwan. We're both technical support specialists here at Autodesk. And we're going to be covering buckling verification using Autodesk Simulation Mechanical. And today the focus, as I mentioned, is on buckling. And before we get into that, I wanted to share some information with you that came from the product team. We have the Simulation Mechanical 2017 beta that is available, and it is found on the forums. And I'm going to post a link here in the chat window, so if anyone is interested, product team invites you to check that out. So here is a link to that. And you'll see, let me present that to everyone. So you can check that link out at your leisure. It's not going to be required for anything we're covering here, but there is some new functionality that's available, so I really invite everybody to check that out, give it a whirl, and let us know how you feel about it. If there's any defects, you can raise those to the development team right through the beta interface. And next we're going to cover the primary topic today, what is buckling, and then we're going to go over the workflow for how we want to do a buckling analysis, some of the items that we want to cover, and along with limitations and advantages of some of the analysis types that we're going to be using. All right, so what is buckling? I'll just fire off a poll question here. I want to gauge the audience's expertise with doing buckling analyses, make sure I'm speaking to the majority of the crowd here. So if you just want to select the level that you feel comfortable with, some of you, I'm sure, do a majority of your work with buckling analyses. Some of you probably use it every now and then, and some of you may be aware of it and have not done it, and a few of you may just be looking into using the Simulation Mechanical product. So I want to welcome everybody. We'll just give that a few minutes to let everybody select their option, and I'll read off some of the results. It looks like everybody has voted for the most part, and it looks like a majority of the people do this now and then. They probably have some confidence in it and are just looking to learn a little bit more. So that's what we're going to be covering today. We're going to be going through the information for buckling and then going through a live demonstration with Marwan. So just a little bit of information about the Euler buckling equation. This is used for the linear solution. So you can see some of the terms that are used in here and how they influence the buckling load, or F. Buckling's an interesting phenomenon. It's used to capture the load capacity of a structure, and something that makes it unique is that you can have this buckling where you have a reduction in the load capability without impacting the materials. So you can certainly have material yielding, but it's not required. So, and then we also, for Simulation Mechanical, offer two solutions. We have this linear solution, often referred to as the eigenvalue solution, and then we have the more advanced nonlinear capabilities. So how are we going to do our analysis? We're going to cover a little bit of the workflow. This is just our approach that we guide users to. You're certainly it's acceptable to develop your own methods, but this is something we guide users to doing based on some of the questions that we get in technical support. We're going to cover the limitations to each of those as well as some of the advantages. And part of doing a buckling analysis, we want to have the most efficient solution process and organizing our workflow so we can get there. We want to start typically by doing a linear analysis or that eigenvalue buckling solution, and then from that we can gather the critical buckling load as well as some shapes. There's some other information that we get that's really more of a qualitative result as opposed to a quantitative result. And then from there we can use that information and do a linear static stress analysis. And this will give us some of our stress output that we're interested in. And one of the things we're looking for there is material yielding, to see if we need to consider that. Based on the outcome of that, we can determine whether or not we need to do a nonlinear analysis. And a lot of the time we get people trying to do a nonlinear analysis right off the bat. That's usually the most challenging one, and it often takes the most time to do an analysis. So we try to steer people back to doing these linear analyses first in order to save time and just begin to get an answer. So discussing the linear solutions that we have, when you're doing the critical buckling analysis type, you're going to get a critical buckling value. You're also going to get the buckling mode shape. And as I spoke to earlier, you're going to get some additional results. You'll get this displacement result, and I want to emphasize this is merely qualitative. So those values that you are getting are not necessarily real. We're just looking at the shape that we're getting. And then lastly, the linear results typically tend to be non-conservative. And so we want to jump into doing a static stress analysis. So we've determined the buckling load, and now we want to check our stresses to make sure that we are considering any material deformation. And one of the things we're looking for in particular is stresses that are equal to or greater than half of the yield stress of that material. And if they are in that area, then we want to start considering nonlinear effects. That's where we would want to jump to the nonlinear stress analysis. A static stress analysis is very simple, easy to do, typically has very good convergence characteristics. And that leads us to the nonlinear area. This nonlinear analysis focuses on capturing the geometric nonlinearity as well as any material nonlinear response. And one of the outcomes we can get for when doing a nonlinear analysis is the post-buckling response. Some of us are concerned with that, so that's one of the things that we can capture here, as well as doing a more accurate buckling response. And with that note, I'm going to share the second poll of the day. And some of you, since most of us do this from time to time, I was interested in learning what factors that you're considering when you're doing your buckling analysis. So let everybody make a selection. And it looks like a majority of the people are choosing the linear buckling response only or the material yielding. So, and it looks like a few of us are interested in the post-buckling response. So some of the information we'll be covering for the nonlinear will be interesting to you. All right, we'll go ahead and close the poll and show some results. And that's what we got there. Looks like we're split pretty evenly between the first two selections. All right, so here are some considerations for doing a linear analysis. You have limited output. As I mentioned before, it's typically non-conservative. When you're doing a stress analysis, it's important to consider the mesh sensitivity. Anytime you're doing a stress analysis, it's important to consider the mesh. We are looking to capture or know if we need to capture the material behavior that we spoke about. And one of the advantages is the solution convergence. And comparing this to the nonlinear solution types, one of the advantages is capturing that nonlinear material and geometric behavior. We can consider how our load is applied. One of the drawbacks is there can be some convergence difficulty due to that nonlinearity. That's something that you may have to tackle. And we do get a lot of support questions about how to do that. So if you ever run into that, we're more than willing to help you on a support call. Again, mesh sensitivity. One of the advantages is having some improved accuracy. And this last bullet is not required, but in some cases you may need to add some imperfections to your FEA model in order to achieve the buckling response. And I want to emphasize as we go through some of these, as we do this, we're trying to simulate real-world characteristics. So deformed geometry, modifying material properties, those are trying to replicate what you might see on a real part where the part is not exactly straight. There may be some material imperfections. We can also modify the mesh in certain areas. One of the common ideas that we try to do is using a kick load, and that's where you input a load out of plane and try to initiate that buckling. We won't be doing that today. It's a bit of a more advanced technique, but and then also deleting elements. So again, these are all things that we want to try to do. We don't want to arbitrarily add these into our model because that can give us unrealistic results. But we're trying to capture what we might see on a real part or a real structure. So now I'll pass this demonstration over to Marwan, if you're ready.
Yeah, I'm ready.
All right, I'm going to change the presenter here.
Okay. Ooh. All right. I'm going to share my screen with you here. Do you see my screen?
Yes, I do.
All right. Thank you, Dean, for this very good introduction. A lot of points here that you touched on, very important things. I'll add a couple of things maybe to elaborate. So linear buckling, really the failure is usually catastrophic because it buckles before it yields. So you don't have really high stresses. It's basically due to the geometry lending itself to buckling based on a load that's not going to cause very high stresses typically, and it's just going to buckle. When we do nonlinear buckling, you might see larger deformations yielding that is going to lead up to buckling. Just a couple of points that came to mind when Dean was going through the slides and the bullets here. So what we're going to do here is just basically walk you through how you would set up a buckling analysis. So right here what I have is an inventor model just of a pipe, thin walled pipe, and I'm going to send that over to Simulation Mechanical and set up the model. So I'm going to change the analysis type to a linear buckling analysis. That's down here. critical buckling load analysis and hit OK. Let's hit yes to all these. And I'm going to go first to mesh, go to 3D mesh settings. I'm going to do this a little differently here. I'm going to go to options, model, uncheck this so that I get a more uniform mesh. And actually, I'm going to go and create a layered mesh of thin parts because that's what this is. This part lends itself to such a mesh, so I'm going to do that and maybe go with a coarser mesh. It's a nice mesh here. It really captures the geometry. Sets the element type to brick, default element definition. I'm going to edit the material, change that to an aluminum 6061 T6. And hit OK. Let's display that. Actually, I wanted to. Okay, that's. I'm going to select this surface down here and add a fixed constraint. And I'm going to select this surface and add a surface force of -1000 in the Z direction, compressing it. At this point, we can go ahead and click Run Simulation. And actually, I did that. I have that. Well, let's open that. Let's save this file. Save. And let's go ahead and open the one that's already been analyzed to take a look, to save time. So that's the same setup here. And once the analysis runs, well, before we do it, let's just go take a quick look at the analysis parameters, which I set at the default. The multiplier is 1. Everything set to default. There's no gravity or anything like that. And I went with that. Now when we look at the results here, it really gives me 5 modes. But the one that is most critical is usually the first one, which has the lowest multiplier. So this tells me a couple of things. First of all, it shows me the shape, what shape it's going to buckle at due to this load. So that is to be expected. It's going to bow out like this and buckle. And it tells me that the buckling load multiplier is 0.806. That says that I need 0.806 times the applied load to buckle. So this, if my actual load, my real life load is 1,000 pounds, that is not a good thing. This thing will buckle at 806 pounds. So really you want to look at, from a theoretical point of view, at a buckling multiplier of 1 or higher to be safe. You probably want to include some kind of safety factor into that built in. So maybe you want to go 2 and higher. That is up to you. But from a solution standpoint, anything below 1 means that my load is more than what would be required to buckle the structure. So again, in this case, since my applied load is 1,000 pounds and my buckling load multiplier is 0.806, you multiply those two numbers, which means that 806 pounds is enough to buckle this pipe. And that's what shape it's going to have. It's not going to give me any stresses. If you look here, the von Mises stresses and all other stresses are grayed out because we don't stresses. The displacements, again, these are basically normalized displacements. They are, like Dean said, more of a qualitative than a quantitative entity, but that's very good. We see the shape that it's going to buckle at. So if we go back here, actually, let me open the model to go through the setup of a linear analysis, and then we'll look at the linear stress. So that's a model, or maybe not. I opened the same model, it seems. Nonetheless, let's go back here and go to the static stress load case. So that's also set up in a very similar way, where it's constraint down here fully constrained, and the load up here is that 1,000 pounds in the negative z direction. Now if I run that as a static stress with linear material models, I'm going to get actual displacements and stresses. So my displacement, if you remember a minute ago, they were 1 point something. Now they are 0.02. These are actual displacements. And I don't see my model blowing out like that. And the stresses are, the maximum is 11,000 psi down here. And if I look where it actually buckles here in the middle and then inquire on one of those nodes, my stress is not much lower. It's about, let's say, 10,000 psi. And you need to do that because you're not sure if what's going to do you in is buckling or actual high stresses. In this case, the stresses are low, but you always want to do a linear stress analysis to make sure, I mean, it could be safe from a buckling standpoint, but you could have very high stresses that you're not willing to live with, that exceed the limit that you set for yourself. In this case, these stresses are about up here, let's say 10,000 psi, which might be perfectly acceptable, I think. So you always want to do both linear buckling and static stress to check for both modes of failure due to high stresses and due to buckling. So this tells me that I'm okay with the stresses, but even though my stresses are not that high to cause any failure, my buckling multiplier is 0.8, so I'm going to buckle before I fail due to stresses. So if indeed my load is 1,000 pounds, this thing will buckle and not a safe analysis. Now if we, let's actually copy this design scenario. Let me set it up for an MES just to go through the setup. If I actually go and change the analysis type to nonlinear MES with nonlinear material models, it's going to ask me if I want to create a new design scenario. I'm going to say yes. And in this case, you definitely want to go in, if you want to use nonlinear materials, by default, it goes with the linear material, the isotropic. So you want to come in here under element definition and change that to a nonlinear, something like a von Mises, with isotropic hardening under plastic. And anytime you change the element definition, you actually want to go in and verify your material so it reads in the yield stress and the strain hardening modulus. The constraint is the same. I'm going to go into my load here just to edit it and verify it. Load curve is, actually I will use a different load curve. I'll change that under analysis parameters setup here. Oh, wait a minute. How did this happen? Oh, here. Cancel. Let's go to analysis parameters. And for this, I'm just going to have a linear load curve 0, 0, 1, 1. Like that. And I do want to go into the output and check output results of all time steps. And you will see why. In this case, I have 20 steps. And really, when it starts to buckle, it's going to cut back on the step size. And you want to be able to capture that. And you will see that in a graph. And at this point, I can go ahead and run the simulation, which was done over here in this MES buckling. So that's the same. No. Oh, actually this one here, no side load. This actually doesn't need a side load, the kick load that Dean mentioned. So this is the same setup that I just did now with the load and the constraint down here. And if I look at the results, first of all, this is the shape. And if I look at the curve, what I did here is I grabbed a node over here, and I can do that again here. I'm looking at the Z displacement. If I select a node, right-click, grab values, so I can see how it behaves versus time. And this is going to tell me when buckling happens. And you can see it happens a little over 0.8. So this is basically predicting the same thing as our linear buckling analysis predicted. So as you can see, the displacement in the Z direction, in the direction of the applied load, behaves in a linear fashion. And once it reaches buckling, it's going to basically take a nosedive. And typically what happens is the analysis is going to start cutting back on the time step size, and you will eventually stop the analysis yourself and not wait for it to finish on its own, because it will, again, typically take a very long time to finish. And that's why we see that the time here is 0.838. That's when I manually stop the analysis before we reach time equal to 1, because we've seen what we wanted to see. There's nothing to be gained from this point on. Actually, it could have been stopped somewhere here. And it's obvious if I draw a box here and zoom in, somewhere over here is when buckling started to happen. And it literally goes downhill from this point on. I can see that the displacement just goes way out.
That's a good point, Marwan. What we're seeing there is the difference, the transition from that axial stiffness to the bending stiffness response. So that's when we can determine when that buckling occurs.
And maybe we can, just for curiosity if you want, we can look at the von Mises stress here. Maybe select the node over here and grab that. And it's going to be basically the opposite. You know, the stresses are going to start shooting up. And, you know, you're going to start failing. I'm not sure what the yield stress is for this material, but we can easily check. That's 40,000. And that's just an example node in the middle. But our maximum stress here, yeah, so it yields and just kind of flattens out for the stress. It doesn't go up too high. If this was a linear material, you're not going to see the same behavior for sure. You can see the stress is just going higher and higher and higher. So whenever you do a nonlinear analysis for the buckling, you want to make sure that you actually select a nonlinear material so you can capture that yielding. Otherwise, you won't be able to capture the yielding. Just out of curiosity, in me making this model, there's a load case here where I actually applied a little bit of a side load. And if I look at the results here for comparison, let's undo the zoom. It happened before. So that load caused it to buckle a little earlier than it normally would have, which is a little over 0.8.
And that's good. You can see how applying a secondary load can influence the buckling behavior, which you may or may not want to see. And in some cases, models that I've ran where you have to apply that, you'll never actually see that buckling response. You'll see some stress accumulation near the boundary constraints typically, and it'll go way past the yield stress for the material, but you'll never actually see any sort of buckling behavior when doing the MES solution. So just something to keep in mind there.
Another thing you can, so this model here really didn't need help to buckle as an MES, as a nonlinear analysis. Just due to its geometry, certain geometries you would need to apply that load, otherwise You won't attain that buckling state. In other situations, what could happen in real life is you have a structure, and it gets loaded in a certain way that produces some kind of a permanent deformation, which will cause it now to have that geometric imperfection that's going to cause it to buckle. Otherwise, it wouldn't have buckled. Otherwise, the structure is stable, but something, let's say, impacts it, causes some kind of permanent deformation, and now it's basically shot. It wouldn't be able to support the loads it's supposed to support, because you got that imperfection that's going to cause buckling to initiate. So if you wanted to do that, what you can do, you can take any MES analysis, really any analysis. It doesn't have to be a nonlinear analysis. But what you can do is you can load it whatever way you want. Let's say we have this shape here, and you can create a new model that is based on the deformed shape. So what you might want to do is a linear or a nonlinear analysis that's going to capture what that impact does to your model, be it, let's say, nonlinear, but will cause it some kind of a permanent deformation. You can model that process and get that deformed shape that is going to be much easier to buckle, and use that as your starting point for either a linear or a nonlinear analysis for buckling. So how would you capture that deformed shape and use that as your new model now? Well, that's easy. Like I said, you can do that for any kind of analysis where you have a deformed shape. The one thing you want to make sure of is under displaced options, you have the scale factor set to an absolute value of 1. So you are actually capturing the exact, well, in this case, it's a bit too much, but anyway, good for demonstrating the idea here is, again, you want to show the displaced model, you want to set the scale factor to an absolute value of 1, and then you go under results options, tools, and click on this make FEM, and you can give it a name and say deformed, and you hit save, and what that will do, it will create a new model based on that deformed geometry, and you can use that as a basis for a new analysis, buckling or otherwise, any other kind of analysis. So that's one more thing, or one more situation that you might find that you want to do, if that's what really happens in real life. Let's see, anything else, Dean?
I think that's about it.
Again, what I want to stress is you really want to go into the setup parameters and check under the output tab, check output results of all time steps, because that by default is not checked. Otherwise, you wouldn't be able to capture, and you can see that here, these points that are next to each other, that's when it cut back on the time step size, it saved them. Otherwise, the time step size is 0.1 seconds, as you can see here. But once the things start happening, which is what you want to capture right here, it wouldn't be able to capture that for you. The critical portion of the analysis won't be captured unless you check. It will be calculated but not saved, but you want it to be saved and displayed so you can determine when buckling happened. Another point that I wanted to mention here is, and Dean mentioned that, the post-buckling, and something simple like this, the pipe, there really isn't much to see post-buckling. It just buckles. But you might have a structure that, one component buckles, and even though it buckles, it's not catastrophic to the entire structure because some other components of that structure will catch it, will bear the load. So you might want to see that as well. So let's say, it buckles, one element buckle, not FEA element, but let's say one component of the structure buckles, but the rest of the structure is going to catch it, but obviously it's going to experience higher stresses. So you want to look at that case and say, okay, well, can I live with that? Or it's okay for now, but I need to do something about it, or I can forget about it. So that's, you might want to look at that. It's all I have to show myself here. We will.
Great. And I think the important thing here, kind of the 1,000-foot view is the process that Marwan walked through as we went from the critical buckling to the static stress analysis, some of the reasons for that, and then jumping into the MES analysis. And so to us, that's the most efficient workflow. You're getting results along the way. As a troubleshooter on our support side, I deal many times with people that are trying to do this MES analysis, and they run into all kinds of issues with the model setup, and it's just very challenging. Stepping back to that critical buckling solution type can help you overcome that, help understand your loads and the behavior as more of a process. So that's our recommendation. And then as you become to get more comfortable, we have users that don't always find that they need to do this nonlinear solution. Once they've done it once, they feel comfortable going back to that linear solution and just running those. So.
Yep.
All right.
Change the
Does
presenter.
anybody? Sure, I can change back to myself, and while we're doing that, does anybody have any questions? You can feel free to input them in the chat window or the question block. And just to emphasize how fun buckling is, it's a pretty challenging problem, but it can be enjoyable, especially when you get some valid results that you feel comfortable with. And as I mentioned here, we have kind of the path for doing the linear or eigenvalue-based buckling, the nonlinear buckling, and then looking at post-buckling response in the MES analysis if you need to go that far.
Okay, do you have any questions here? No?
We did have one question from Jeremy. He was asking, does buckling analysis work with shell elements? It does. And as I mentioned in the window there are some element types that are available for MES that aren't available for the linear solutions. So I mentioned the pipe element, for instance. It's kind of useful because it's easy to apply some of the loads that you would see in pipes. But other than that, it's not necessary. And we have a question here. So is that right to say MES captures buckling automatically? Are the amount of stresses and displacements correct with MES?
Yes.
And I would say yes as well. One of the things that you may consider, like Marwan showed in his model, we're looking at that plot. Sometimes that break between the axial and bending stiffnesses is not as clear. You may not have that sharp break. That's more gradual, so it's difficult to see or interpret when that critical buckling load is. And so that's where you may have to play with your mesh size, look at your loading and how you're applying it. May also have to add more steps to ensure that you're capturing enough information when that transition occurs. So again, I would say yes, but there, along with doing a nonlinear analysis, you have some other factors you need to consider.
The usual considerations, basically.
Usual suspects.
Yes.
Perfect, and it's pretty quiet, so I think we're about 22, the top of the hour, so we'll hang on for another minute here, but I want to thank everybody for coming to today's webinar. We enjoy presenting on this information. And All right, it looks like we're quiet. No one's asking any more questions, so we'll go ahead and wrap this up for today. And oh, we had one more come in. Is this done using Nastran? No, this is done using Simulation Mechanical, but we also have the Nastran solvers available for the critical buckling. So you can do this with Nastran. I've done some verification, and the results are very comparable across both platforms. So you can also use the Nastran editor as an option as well. That gives you some different solution types there, the nonlinear and nonlinear transient. So you can certainly use that if you feel the desire. All right. We have one more question. Marwan, I wonder if you can speak to this, if we can combine the response spectrum and buckling when
Important
considering
for.
columns and
Uh, Not really. I mean, there are two different analysis types that really don't lend themselves to. And I'm assuming you're talking about the load combination here. Um, as far as the load combination, no, you can't combine these two different analysis types. But if you're talking about with the response spectrum analysis capture buckling, I would say no. No, they would have to be done separately.
great question.
Mm-hmm.
Yep, this webinar will be available. We'll send out a link along with a description, and we post all of these to YouTube. So if you have a link to one of them, you can do a search for the other ones on the Sim360 channel. So definitely. We'll also make the PowerPoint available so you can scan through, and I'll try to get the models that Marwan used so you can use those on your own. Cool. Well, if anybody else has any questions, feel free to contact us via the normal support methods. We look forward to hearing from everybody, and we'll go ahead and give you back 15 minutes of your day.
Thank you, everyone.
Awesome. We'll see you next time.